Hello there, Mr. Sutton here, bringing you this lesson on motion and position. In this one, we'll be finding the displacement of an object in motion and the position and or velocity of a particle at a certain time if we already know their rates of change. For this warm-up problem, we have a particle moving along a line with a velocity given by this v of t function in feet per seconds. We want the displacement of the particle from the interval of 1 to 4, and not a calculator problem here. So pause the video and see if you can figure out what they're asking for here. All right, now displacement, you've seen that one before. Displacement is basically how far you ended from where you started. Not necessarily how many steps you took to get there, but basically where you ended up minus where you started. So we can say that displacement is the net change in position, which, since velocity is telling you how your position is changing with respect to time, we need the integral of velocity to get the total change in position, to add up all those little distance changes. So we're going to take the integral of v of t from 1 to 4, and now taking my antiderivative, because I can't just plug it in the calculator, it's a no calculator problem, we have, this is going to be negative t cubed if this bumps up to a 3 and we divide by 3, so negative t cubed, plus this is going to be t squared from 1 to 4, so that's all this stuff with 4 plugged in minus all this stuff with 1 plugged in. And now we've got negative 64 plus 16, that's negative 48. In this other brackets here, this is negative 1 plus 1, which is 0. So negative 48 then ends up being our final number. Now what are the units going to be on this? Well, it's displacement. That's a distance kind of change, so this should be in feet for that reason. But even if you couldn't figure it out from just knowing what displacement is, if you look inside the integral here, velocity is in units of feet per second, feet over seconds. This little dt differential is an infinitely small change in the input, in time. So you have feet per seconds times seconds. Seconds is canceling, leaving you with feet for your units. For this next example, which is calculator-based, we have a particle moving along the x-axis. Its velocity function is v of t for times greater than or equal to 0, and position at time 0 is given down below in this the rest of the problem here. So here's v of t, here's the starting position. The first thing we want to do is figure out the position at time equals 4. So we've already talked about how to find the displacement using the velocity, figuring out how far away you've gone from where you started. So we can use that concept with a starting value to find new values. Specifically, our position at any given time is just going to be that starting value plus the displacement. Starting value plus how far you went and maybe a sign to tell you which direction. With that in mind, pause the video and use your calculator to see if you can figure out where we are at time 4. So to get the ball rolling on this with the calculator, I'm going to first enter my velocity function into Desmos. So we've got v of t and 3t squared minus 40t plus 100. All right, so we'll use that in a moment. So my setup, I'm going to have my starting value of x of 0, which is negative 2, and to that I'm going to add the displacement from time 0 to time 4. So that's going to be the integral from 0 to 4 of this v of t dt. And this is exactly what I'm going to plug into my calculator now. So going back to Desmos, let me just go down to a new entry, and we're going to do negative 2 plus integral int from 0 to 4 of v of t dt, and that comes out to exactly 142. Now they didn't give us units here, so we're not going to give them units back. We're just going to write 142. For the next part of this question, they're asking if the particle is moving away from or toward the origin at the time given above, at time 4. Okay, so the idea behind this is we have to compare the position and the velocity. If the signs of x of t and v of t are the same, so if the direction that we're going based on the velocity and where we are with respect to the y-axis based on x of t, if those are the same thing, then we are moving away from the y-axis or the origin. Now, if the signs are different, if x of t and v of t have different signs, let's say I had a negative x value and a positive v value, Since they're working against each other, we would be moving toward the origin at that time. So with that in mind, pause the video and see if you can figure out which way we're going here. All right, so the only missing piece that we have if we're doing this analysis is what v of 4 is. We have x of 4. We just found it's 142. It's positive, but we need to know what v of 4 is. So let's go back to the calculator, and let me just punch in v of 4 down here, just so we can see it. That's giving us negative 12 back. So the key on this is that this is a negative value. Since v of 4 is negative, and x of 4, positive 142, is positive, since those two have opposite signs, in other words, that's the second case where the signs are different, so we can conclude that we are moving toward the origin.
On this problem, we're given a particle with an acceleration function, a position at time 3, and a velocity at time 1. Based off this information, we want to work our way backwards to find the position function. All right, so our strategy on this one, we're going to have to go from acceleration to velocity to position. So we're going to use some diffie-q here. Diffie-q works really well if you have two levels that you have to go, finding functions, or if you're not allowed to use a calculator. If you are allowed to use a calculator on only one level, then FTC works a lot better. But for this, we'll use diffie-q just to show you another way to do things. So strategically, we're going to use diffie-q on our a of t here to get our velocity function, and then we're going to use diffie-q on our velocity function to get our position function. So let's start with the getting our velocity function. We're going to take the antiderivative of both sides of this acceleration equation here. So antiderivative of the left side is going to be v of t. V of t is the antiderivative of acceleration, because acceleration is the derivative of velocity. On the right side, we've got 3t squared minus 20t plus c. Now, I'm going to have to go two levels of diffie-q here. So I'm going to call this C1. And now we're going to go about trying to figure out what C1 is. Well, to do that, I need an initial velocity value. Now, they told us that when time is 1, velocity is 3. So I'm going to write 3 equals, and then all of these t values with 1 plugged in for those. So on the right side here, I've got 3 minus 20, which is negative 17. Adding that to the left side, I have 3 plus 17, giving me a C1 value of 20. So that means my velocity function is 3t squared minus 20t plus 20. All right, we're going to go one level below that to get the position function. Pause the video and see if you can get from the velocity function down to s of t, the position function. All right, so our first step, again, antiderivative on both sides. So we've got s of t, the antiderivative of v of t, and that equals, from left to right, let's see, this bumps up to a 3, dividing we have t cubed. This will become minus 10t squared plus 20t, and you guessed it, we're going to add c1, or c2 rather, is our constant, c2, because we already used c1 up there, so this is a different constant. Now we have to solve for c2 in order to get our position function completed. So I have a position of 10 when I plug in the t value 3, so I can write 10 equals 3 cubed minus 10 times 3 squared plus 20 times 3 plus c2. What's all this craziness add up to? Well, let's see here. We've got 27 minus, this is going to be 90, so that's going to be negative, let's see, 63 plus 60 is going to be 123. Well, actually, it's negative 63 plus 60, so that's negative 3. Adding that over to the left side, I have 13. Whew, mental math. And then plugging that back in, we've got t cubed minus 10t squared plus 20t plus 13. Boom. For this last example, we have the graph of the velocity of a car traveling on a straight road given up here. And then we have a table of values for v of t at 5-second intervals given over here. So we want to approximate the integral from 0 to 50 of v of t dt with a Riemann sum using midpoints of 5 subintervals of equal length, and then using correct units, explain the meaning of this integral. All right, pause the video and go ahead and find that Riemann sum to start with here. So for the integral from 0 to 50 of v of t dt, we can say that is approximately equal to, notice the approximately equals, Now we need a midpoint Riemann sum, subintervals of equal length, 5 of them. So we have a subinterval from 0 to 10, 10 to 20, 20 to 30, and so on. So we're going to use all the halfway points to get the y values out of this. So my first base times height rectangle area I'm doing, I have a base of 10 times a height of 12, because again, I'm taking that middle value. Then I have a base of 10 times a height of 30, and then 10 times 70, 10 times 81, and finally 10 times 60. Now, in terms of units on this, we just figured out the integral of velocity, which we know is displacement, which is measured in this case, feet. So you actually could stick feet on all of this and be done with this part of the problem. If you actually wanted to add all this stuff together, it's not necessary, but I guess if you needed to, you could factor out a 10 and add all the stuff inside. So 12 plus 30 is 42, plus 70 is 112, plus 81 is 193, plus 60 is 253, times 10, there you go, 2530 feet. Didn't have to do that, though. But what you do have to do, they wanted you to explain the meaning of this integral. So what does the integral of velocity from 0 to 50 actually tell us here? So integral of velocity is going to be the displacement of our car in feet. And now in order to get full credit on this, you have to give the time interval. So from 0 to 50 seconds. If you're missing that time interval, you don't get the credit. Notice also that I said the displacement of the car. On this particular problem, since we know that our velocity is positive the whole way, meaning we're not actually changing directions, this displacement also happens to be the total distance of the car. But this is not always necessarily the case, because you could have a car that's driving forward and then backwards. So just to be on the safe side, I called this displacement, not total distance. We'll deal with total distance in another lesson. So that's all for this one. Thanks for going the distance with me. Till next time, Mr. Sutton signing off.